Hey kids, Smith here. Welcome to chapter 17, Thermodynamics. Now we're going to be talking about energy and heat and temperature changes and phase changes. It's got a pretty cool mix of qualitative and quantitative. So this video is going to be introduction about what it is we're doing, and the next video should be examples of the calculations that we're going to try to do. There are a fair amount of calculations towards the end of this chapter because energy is very important. We want to keep track of that. So let's talk about thermodynamics. Thermodynamics, by definition, is the study of energy and all of its interconversions that are going on here. By interconversions, we mean that if we take a hot piece of metal, put that into a beaker of cool water, what's going to happen? The metal's going to cool off, the water's going to heat up. That energy has been converted from the metal into the water. Or suppose I take a beaker of HCl, a beaker of sodium hydroxide, mix those two together, they're going to generate a certain amount of heat. That's a heat of solution. We're converting that energy from one form, chemical, probably to another form, thermal or heat. We're going to be measuring that temperature. Now, there are a couple laws of thermodynamics that we really got to follow, not just like speeding laws that are maybe suggestions or recommendations for some of you, but these laws, the first one of these is the first law of thermodynamics. Now, there's actually a 0th law of thermodynamics, but all it is the transitive property that if the temperature of one thing, or this thing has this much energy, and this thing has this much energy, well, then those two things have the same amount of energy. A is equal to B, B is equal to C, therefore A is equal to C. It's kind of that transitive property. We're not going to go into too much depth about 0th law here. We don't need to. But the first law, we're going to go into. We've got to follow the first law of thermodynamics. How come? Because in this house, the laws of thermodynamics will be followed. And the first one says, you may not create nor destroy energy in any way, shape, or form. Now, as soon as we say that, and I make such a big deal out of it, this is going to obey as long as we're talking about chemical reactions. If we start talking about nuclear reactions, then this goes off the table. We're going to lose a little bit of mass, and that mass is going to be converted to energy. If we lose a little bit of energy, it might be because we converted it into mass. See, that's what E equals mc squared lets us do. It lets us convert energy. But for our purposes, if we have a chemical reaction, first law of thermodynamics is going to hold true. We're going to convert energy. We're going to change it. I already explained that. That energy is probably going to be transferred in the form of heat. Heat is simply that, the transfer of energy from one form to another. Is it possible for two things not to transfer heat? It could be. We're going to call those things, pretty interesting that you asked, not that you did, but we would call them isotherms. Something that was at the iso means the same therm, the same amount of energy. Pretty rare for something to be isothermic because, to be honest with you, they would have to be made of the same material, have the same amount of material, and be at the same temperature. That's going to be relatively unusual, but we could have it happen. Now, this heat that we're talking about, we're going to represent that with a lowercase q. Q is equal to heat. Heat always flows from the hotter thing, higher energy, down to the colder thing. So if we take an ice cube out, put an ice cube in my hand, the energy is going to flow from the high energy, my hand, into that ice cube. It's going to flow upwards from my hand into it. Always flows from the warmer thing into the colder thing. And so the warmer thing is always going to be losing energy. It's going to be getting negative. Now we say that that's Q. Eventually we're going to introduce something that's called enthalpy. Enthalpy is the same as Q. And so I'm going to put this in here now just so that we don't have to deal with it too much later. but Q for our purposes is pretty much equal to delta H. That delta H is enthalpy. Now, to examine that heat flow, we're going to need to define an area of study. And that's this system and surroundings that we're talking about out here. The system is the area that we're studying. In our case, it's probably going to be a solution that's inside of a test tube or something inside of a beaker or a reaction that's going inside some vessel. But that's going to be our system. And then the surroundings is everything else around that vessel, everything else that's in the room. And so right now, I could have my Diet Coke going on, and my Diet Coke is cold. So what's happening? That's my system, and energy is flowing from the room into the system. All right? This is absorbing energy, gaining energy, getting warmer as we go. Okay, that system and surroundings is totally flexible. We define that. For our purposes, we're chemists. We want to be defining it in terms of test tubes and beakers and flasks. If we're working in physics or even a much bigger scale, let's say we're working in architecture and our job is to be heating and cooling buildings. Well, then the whole building is our system. And our air conditioning and heating system has to take into account that whole system. What's the surroundings? Everything else in the world. Okay? If we take the system plus the surroundings, we end up with the universe. We don't really have a choice. Something is either going to be part of the system, that area which we're going to study, or it's going to be surroundings, everything else that doesn't get studied. Okay? Now, when we think about that, we have terms that are going to help us describe. And in this case, these terms are called exothermic and endothermic. And I think we've talked about these a little bit already. Endo, as the name implies, in. Heat's going to flow into the system, and it's going to feel cold to us. So when I grab my Diet Coke, it feels cold to me. Why does that Diet Coke feel cold? Well, heat's flowing from me into it. Heat is going into the system. Conversely, if I had my coffee mug and I've got something hot, heat's going to go from the coffee mug into my hand. Now that's exothermic. Heat is going out of the system. Remember, we always think about things in terms of the system. So you got to shrink yourself down really small, hop inside of the Diet Coke bottle, hop inside of the coffee cup. Imagine yourself in the system and then figure out whether it's positive or negative. If it's endothermic, then we're going to have Q equals positive. Endothermic. When Q equals negative, it's exothermic. And that should make perfect sense. The system is losing energy, therefore it's negative. That's exothermic. The coffee cup is losing energy. The coffee is giving off its energy to my hand. So Q of the coffee or of the coffee cup is negative. Now, that's my flow of energy both into and out of. Endo in, exo out. Now, we also have certain things called heat capacity. What that is how much energy do we need to actually raise the temperature 1 joule, all right? How much heat we need to raise the temperature 1 degree Celsius. That's called heat capacity. We all have a heat capacity. But heat capacity isn't very useful for us because, let's face it, the amount of energy it takes to heat up a little itty bitty bottle of Coke would be a lot less than it takes to heat up a big bottle of Coke or coffee or whatever it is we want to heat up or cool off. So instead, we use this term called specific heat. Specific heat is the heat needed to raise 1 gram 1 degree Celsius. Now, a lot of you are saying, hey, wait a minute, I kind of remember something about that. That's right, that 1 calorie, this little calorie, is the amount of energy. This is energy to heat 1 gram, 1 degree Celsius. Now that's calories. Those are not the units we would prefer. Instead, we would prefer to use joules. And a joule is simply that. It is a measure of energy. That's the SI unit. Calories, I just explained that. What's our conversion unit? 1 calorie is 4.18 joules. Now I got to preface, these calories we're talking about, they're not food calories. They're not potato chip calories. Those calories are kilocalories, okay? So specific heat, uppercase C, energy to raise 1 gram, 1 degree. Water has a specific heat of 4.18. Iron has a specific heat of 0.45. So what does that mean? It means it's going to take me 10 times more energy, almost 10 times more energy to heat up water than it would for iron. The lower the specific heat, the easier it is to heat up. It takes a tremendous amount of energy to heat up water. This lake behind me, Lake Bow up in Canada, it's freezing cold in July. How come? Because, well, A, it's Canada, but B, because it is a huge, deep, deep, deep freshwater lake. All right, so it takes a long time to heat up water. How come? Because it has a very high specific heat. We can convert from calories to joules and back and forth. So if we had 25 joules, and we wanted to convert that to calories, 1 calorie is 418 joules. So we get about 601 calories. Remember, not food calories. If we wanted to convert that to kilocalorie or to kilojoules, 18.6 calories, 418 joules, and then remember, it's a kilojoule. So this is not very many kilojoules. Joules are very small energies of heat, so we use kilojoules a lot. Now those are my calories. That's about all I'm going to have to say about calories. The rest of this, we're going to measure things in terms of its enthalpy. And I alluded to this earlier on the front page. Enthalpy is delta H. Delta H is the same thing as Q. Your book uses both, and it's okay. There's a subtle difference. What's the amount of energy that something has? It's going to be equal to the mass, how much specific heat, how much heat it takes to heat it up, and how much do you want to change the temperature. That change in temperature is always going to be final minus initial. Now, this is the theory behind it. This is all the energy stuff we've talked about. Next video, we're going to get in, we're going to start calculating stuff. I'm Smath. This has been a great intro on thermodynamics. I hope this video helped you.